Um, so let's get started. Welcome to the second plasma physics session of the IVS 2020 IVS Plasma Conference. We have exciting talks today. So we have 7 of them. So we try to keep it on time. Since the talks are short, I ask you can keep your microphones muted and virtually raise your hands or use the chat to ask questions. And if you have time, so the speaker can address the questions at the end of the talk. Our first speaker is Nat Fish. I believe I not to be introduced in this forum. I just mentioned that he is the head of the plasma program at Princeton University, received Maxwell and Fenn prizes for his contribution to current drive and more. He will tell us about energy transformation in plasma. And Nat, so the stage is yours.
Hey, thank you so much, Ido, and thank you for the introduction, and thank you for the invitation. It's just wonderful to virtually see everybody. And let me see if I can entertain you for a couple of minutes on energy transformations in plasma. So, let's see. So there's a lot of different energy transformations in plasma. We could go from thermal energy to fusion. That's a good one. We can go from thermal energy to radiation or thermal energy to directed. There's different ways of doing that. You can do it in the other direction, directed to thermal, like in compressing plasma through flows. You can have radiation that heats plasma in the, could be in the RF regime or could be in the laser regime of the frequencies. And you could also have directed energy that produces turbulence through shocks. And then there's, of course, electric and magnetic energy, which can also be dissipated into thermal energy. Gravitational energy, potential energy can be dissipated into thermal energy. And turbulent energy can also be dissipated into thermal energy. And as you can imagine, we can imagine other ways of doing things, radiation to magnetic, radiation to other kinds of radiation, turbulent to magnetic. These are all different energy conservation, energy transformations. And I'd like to just pay a little bit of attention to some unique features of plasma that make these transformations sometimes very curious and very interesting. I've sort of highlighted 2, which is in an electron ion plasma, the electrons have just such a much smaller mass than do the ions. And that's really something special in plasma. And it's also the case in plasma that instead of having hard sphere collisions, you have Coulomb collisions. So that means that the cross-section for the size of a particle goes as 1 over the velocity squared. Cross-section goes as 1 over the velocity to the 4th power. This makes for some very, very, you can almost derive all the interesting sensitivities from these 2 points. Just the Coulomb collision cross-section is unusual, and the species have a very large mass difference. So you can derive, for example, the viscosity is very sensitive to temperature as opposed to neutral gases, which it's not. Now, then, of course, the plasma can also be magnetized, and then because of that, you have very different cross-field diffusion for the different particles, and of course, you have collective motions in plasma. So let me show you how some of these things make a difference. Now, first of all, so what's the big deal of the electrons being much smaller in mass than the ions? Well, it allows you to maintain the species at very different temperatures. How does that work? Well, each species will get to equilibrium fastest when it finds another particle of equal mass to collide with. It doesn't help to collide with a particle of much greater mass or much smaller mass. So electrons have to find electrons, ions have to find ions, but electrons move at about the same temperature. They'll move at a square root of mass ratio faster. So they'll find their other electrons square root of mass ratio faster. So they're going to equilibrate square root of mass ratio faster than the ions. But the energy exchange, that's going to be small in ME over MI because there's not that much energy transferred in each collision. So you have, first thing is the first day of the year, you have the electrons equilibrate among themselves. You got to wait a month for the ions to equilibrate among themselves, and then you've got to wait 40 months for the electrons and ions to finally equilibrate between them. That means that you can have each species get to its own temperature before they equilibrate with each other. Now, why is that important? Well, you can get a hot ion mode. You can get the ions to be hotter than the electrons. And that's something really important in fusion, because the ions fuse, but the electrons don't. The electrons just radiate the heat away, and it also costs and pressure to contain them. So you would like to get the ions hotter than the electrons, and in principle you can because of this separation of time scale. The question is how you're going to do it. Now I'm just going to mention briefly something that I worked on for quite a while, and I've discussed it in forums before, but that's the idea of alpha channeling, something that that makes use of the fact that alpha particles in a fusion reactor tend to have a normal power flow with the heat electrons, but if you did that, the electrons would always be hotter than the ions. So you'd like to interrupt that power flow and use some waves to channel the alpha particle energy first into the ions, and then have the ions heat the electrons. And if you do this, you double the fusion power density. So this would be making use of the fact, again, that it's possible for electron and ion temperatures to come to different equilibria. The question is, how do we do that? Because the alpha particles want to slow down on electrons. And I'll just mention very quickly that there's a way to do it by waves. And that's because the time scale for collisionless interactions can be much faster than the time scale for collisional interactions. You just have to find an inversion in the diffusion path to take hot alpha particles in the center to cold at the periphery, and then you can pull them out and make them cold at the same time. And this is something that I worked out with Jean-Marcel Rax almost 30 years ago, and it's a paradigm that I come to back to again and again. You just shine waves at a confined box of plasma, and if you set it up right, the hot particles can come out cold. Okay, but that requires RF energy to catalyze the hot ion mode. Is it possible to get to a natural hot ion mode? So for example, in ICF, if I started out with the ions hotter than electrons and then I compressed, then the ions would remain hotter than the electrons if I compressed fast enough. But what about in steady state? For example, let's take a centrifugal mirror. So is it possible to just, from the natural configuration, have ions naturally hotter than the electrons? And so now we have, for example, a situation where we have a rotating plasma. There's a lot of energy in rotation. So let's imagine a lot of energy in equal speed rotation. But now there's dissipation because there's viscosity, there are collisions. Is it possible to have a hot ion mode? And the answer is yes, it's possible, but it depends. So you have to look at what at least the classical mechanisms of e-cross-speed transport are, and they could either be frictional because of the local velocity difference at any particular point, or it could be because it's the rotation shear. And then you have viscosity, and the ion viscosity in magnetized plasma, again, because of the mass ratio, is much larger than the electron viscosity because they have larger mean free paths in the direction perpendicular to the field. So you have a situation where you have dissipation that behaves differently, whether it's frictional dissipation or viscous dissipation. And you can get to, depending on whether you have a very peak profile, in which case you'll end up with frictional heating, or if you have a profile that's far from solid body rotation with large shear, then you can get to ion heating. And in principle, you can get to a hot ion mode when you do something like that. I think I'm going to, just in the interest of time, I think I'm gonna skip the actual mechanism of the cross field transport. But it's just, maybe I'll just say that the viscous transport arises directly and you can have charge transported. The frictional transport is ambipolar, and it's only some higher order effects in the gyrofrequency, in the rotation frequency over the gyro frequency that actually produces charge transport and accompanying dissipation. Okay, now I'd like to move to a slightly different paradigm, and that's to store energy in one form and then suddenly release it in another form. And you heard this morning, I heard it too, okay, wonderful talk by Yitzhak Moran, and he talked about these, what I would call very provocative Weizmann-Ziepen's experiments, where he showed with wonderful measurements how most of the ion energy appears as turbulent kinetic energy, not as thermal energy. Now, there's a big difference between thermal energy and turbulent energy. We kind of try to imagine it. Okay, just imagine you have turbulent energy, and you could put the same amount of energy in a box. Okay, but if it's turbulent, you have lots of cold eddies that are rapidly moving around. Most of the energy is in the ion, but it's in directed energy. So that means if I look at any one spot, the ions are not moving relative to each other by much. They're all moving together, in which case it's not going to be fusion. The electrons are also moving with the ions, so that means that there's also not going to be radiation. So basically, you don't have radiation and you don't have fusion, even though you're confining a lot of energy in the system. So it's interesting because it's very different from thermal energy. So now let's ask the question, let's say I've got the box of turbulent energy, mainly turbulent, let's say, and I compress it to half the size. Now I have to answer the question, how much energy did it take to compress this? Okay, there's actually two fundamental questions. It's how much energy it took to compress, but I also want to know the partition after compression of how much of the energy is thermal and how much of the energy is turbulent, because they both behave very differently with respect to radiation and with respect to fusion. So it's kind of interesting what happens, okay? This actually what turned out to be the thesis of Seth Davidovitz. And you have something very interesting. I should say over here that now we're making use of the fact that the viscosity in a plasma, as opposed to neutral gases, is very sensitive to temperature. Temperatures are the 5 halves. So you have an explosive thing happening. You can start out in viscid, where you have lots of turbulence, easily you compress it, you get more turbulent energy, but then you also get more thermal energy. And if the plasma becomes hotter, then at some point the viscosity becomes really large, and then you start to dump the turbulent energy into thermal energy, which is explosive, because then you become even more viscous. And that's what Seth found. So as you compress L, okay, L goes to some smaller and smaller distance. This is the size of the box. You start out turbulent with small scale turbulence. You end up with larger scale turbulence as I go to B, and much more energy. And then all of a sudden you dump the energy very quickly into heat. So that gives us a new ignition paradigm. The traditional approach is to start with temperature, compress, and you increase the temperature. Instead, let's start mostly with turbulent kinetic energy. Now, when we compress, it's cold, so we don't have losses in radiation, and then we'll dump the energy all at once. And you can look at trajectories and temperature, rho R space for an ignition scenario, and you can find that you're keeping the parcel of plasma cold because you're suppressing radiation until you actually need to use, and you need to get to ignition, and then you'll change all that energy into thermal energy. You can imagine that, you can imagine the question, can this operate, let's say, in a proton-boron 11 reaction? Well, if I just look at the scalings of this, if the hotspot ignition is triggered at a Reynolds number of about 1, then I can accomplish higher temperatures which gets me to a more viscous regime by working with, let's say, more boron, which will get me to a more inviscid regime. Now, instead of turbulence, I could also imagine compressing a plasma wave. Basically, I can imagine different correlations in a plasma that I could compress, and you get a similar situation. If I had a Langmuir wave or BGK mode, I can even compress more energy. As I compress it, the Langmuir wave grows up because I have adiabatic compression of the Langmuir mode. But at some point, because the case and the system become large, I suddenly land out down. It's a collisionless damping mechanism now. So, but something that's quite interesting is that the plasma with embedded energy is softer to compress at the same plasma energy. In other words, I can put more energy in my plasma mode without getting to higher pressure. So let me go just a little bit further with this paradigm. Okay, let's make use of the fact that the collision frequency is a very sensitive function of velocity. So that's the basis for RF current drive. That's also something I've worked on a lot. And the point is that if I push particles in, let's say, parallel to the magnetic field, from velocity space location 1 to velocity space location 2, possibly in the direction perpendicular to the field, because they're more collisionless when they're in velocity space location 2, they'll carry their current longer. So that's a big thing for a current drive effect. When people did experiments, they found that there was a huge, because we're talking about energy transformations now. So they found a very large efficiency of transferring the RF power into magnetic field energy. So in other words, RF energy to magnetic field energy was upwards of 20%, sometimes as high as 40%. It was hard to understand how it could possibly be so efficient. And the reason is because when I push particles with a wave from one space location 1 to space location 2, if I do it against an electric field, I'll put the energy into the electric field. If I do it against collisions, I'll put the energy into collisions. So if I work far enough out in velocity space where there are not so many collisions, I'll put most of the energy into the electric field. And why is this important? I mean, for current drive in a tokamak, you have the opportunity to recharge the tokamak at low density when the efficiency, when the collisions are very low, and it's easy to put all the energy in the electric field. Then I can increase the density in the plasma afterwards, and that means that I can get a lot of fusion out, for example, but I'm not changing. At that point, I shut off the RF, and I just let the plasma coast at a higher temperature, and I'll get the benefit of that over a long time. So I cycle, so basically what I do when I put in the RF, I'm opposing what I'm putting in by, I could have a larger ion charge state to oppose it, for example, and I'm making it very efficient by having a low density. And then when I do it like this, I can get factors of 10 in the average efficiency, 10, 20 easily. These terms are all multiplicative. So the final thing I'm going to mention, okay, because I know I have just 1 more minute, or 2 more minutes, and that is something that's also very interesting about plasmas, okay? On the ion, again, because of the difference in the mass, the electron and ion masses, on the ion time scale. So in other words, if we look for collisions in a magnetic field, charge transport in a magnetic field, the ion, you have to transfer momentum in the ions. That will occur MI over E, square root of MI, square root of a mass ratio, faster than for the electrons. So that means that, on the first day of the month, I'm equilibrating ions, and then it takes another whole month, 40 days, for the electrons to participate. That means that, and then in a magnetic field, because I can't move charge around by collisions, I have charge incompressibility. So now I have a very curious type of substance where it's compressible in density, but it's not compressible in charge. So if I have a gravitational field, so here's my magnetic field into the board, and I have a gravitational field. I don't really mean a gravitational field for general applications. I mean a centrifugal field, but it's the same as a gravitational field. Then I can get a very curious sedimentation where the heavy particles could go to the top and the light particles could go to the bottom. It all depends on the charge to mass ratio. It could go in either direction. And the interesting thing is that wherever the charges with the less charge go, the ions with the less charge go, they have to be more dense, so they get compressed. So I have compressional heating of the charges that are of the ions that have little charge, and I have because they have to take the same space as whatever charge the higher charge ions had before. The higher charge ions now take up more space, so they're cooled. So this is a new heating effect. We published it this year, and it goes in the same direction as the ion-ion Edenhausen effect, which is also a way of transferring charge. So, okay, let me summarize. Okay, there's unique features of plasma. The particular ones I made use of was that there's a huge mass ratio between electrons and ions. And also that there's a very interesting, very sensitive dependency on collisions on velocity. And that allowed us to get electrons and ions at different temperatures. It opened the possibility for hot ion mode. We could catalyze that with waves. We could retain it under compression. And in an E cross B rotating system, there's ways of actually getting to that in sort of naturally by using viscous dissipation as opposed to a frictional dissipation. Now, we could also use, again, the viscosity dependency that's very sensitive in plasmas is also that comes again out of ME much more than MI, and also from the Coulomb cross-section. And that allowed us to get a sudden dissipation effect that we could use for fast ignition or faster radiation. We could have some similar thing to that if we compressed waves. Then we could also convert RF energy to magnetic energy and exploit, again, the adiabaticity of the waves. We could go, let's see, I forgot to change this over here, but I'm exploiting the fact that the Coulomb cross-section is much smaller. It goes as 1/v cubed. And finally, there was a heat pump effect in magnetized multi-ion plasma, which exploited the very curious thing about plasmas on multi-ion plasma on a short time scale, in that you're incompressible in charge, but you're compressible in density. So when you're trying to compress this kind of thing, you can't compress the charge, but you can compress the density and you get some very curious effects, including a heat pump effect. So I'll stop over there, and thank you very much for paying attention.
Thank you, Ned. So since we are over time, we will go our next speaker, which is Eli Sarid, who is the same researcher from at the Sorek and faculty at Ben Gurion University, and a member of the Alpha collaboration at CERN. And he will tell us about recent exciting experiments on the physics of antihydrogens and antimatter at CERN. So Eli, please go ahead.
All right. Hello. I'm really happy to participate in this virtual conference. And I remember today that it was this month, 15 years ago, that I got the mail to join the collaboration in CERN. So it's been quite a long way. At the time, it was just an idea to make the equivalent of the hydrogen atom, which has the proton and the electron as an atom, and to replace them in the antimatter equivalent with antiproton and positron, and not only to make it, but to capture it and to measure its properties. From an idea, we made a long way over these 15 years, and I will briefly summarize where we are today in this 15 minutes talk. Along the way, the participating institutes that I belong to were NRCN and Sorek. There were also collaboration with a group from Hebrew University at the time with Professor Lazar Friedland. Andy Dobart was a PhD student then, now is the chair of our session. Then there was a collaboration with BGU and with Professor Gedalin and our students Nir Cohen, and now with Nir Davidson group at Weizmann. So Alpha is a collaboration that is made up of groups from 15 or so institutes, about 40 to 50 scientists, and it is a very multidisciplinary group. You see here groups from all over the world, especially America, North America, Brazil, Europe, and Israel, with the NRCN and SOREC, the participating institutes. This is how it looks, how it looked at the CERN press release in 2016, where CERN said that the achievement at that time, that when we first measured the light spectrum of antimatter, they call it a completely new era in high precision antimatter research. And this new era is where we are today. So what we are asking, we ask several fundamental questions about the properties of antimatter, and the expectation, the theoretical expectation, is that atomic levels, transition energies, even gravitational behavior will all be like what we find in the normal matter hydrogen atom. Specifically, the atomic levels and the transition energies, the predictions that we will find exactly the same results as in normal hydrogen atoms are a very basic prediction of the CPT theorem. So even the slightest violation of this identity will cause a physical earthquake. All of these questions on antimatter are at the bottom. The big question is how come we are here? Because the small inequality of matter and antimatter in the Big Bang causes the universe to exist as we know it today. So antihydrogen does not exist in nature, and the fact that all collaborations interested in antihydrogen come to CERN are because this is the only place in the world that can supply a beam of antiprotons. So the basic experiment is get the beam of a 5 mega electron volt before of antiprotons. From this year onward, it will be 100 kilo electron volt. So we talk about mega electron volt, kilo electron volt. We have to slow it down really to low velocities, temperatures, and combine it with positrons that come from a radioactive source of sodium-22. The plasma topics that come into play here are because all these manipulations that we have to do for the antiprotons and the positrons, there are non-neutral plasma manipulations that that were developed in groups like in San Diego, in Berkeley, two groups that I worked with, and elsewhere. But eventually, when the atoms are hopefully produced, the antimatter atoms, then of course we go into a different discipline of how to trap neutral atoms. And this is done by a magnetic trap. Non-homogeneous magnetic field interacts with the magnetic magnetic dipole of the atom. And then the trap that you see here in this figure is very shallow. For every 1 Tesla field difference that will apply between the center of the trap and the wall, will get less than 1 Kelvin of the depth for the potential well. So unless the atoms are colder than 1 Kelvin, they will not be trapped. So you see here the picture of the experiment. You see the very dominant presence of the cryogenic helium vessels that are brought into the hole. This is not although we are in CERN, this is not a high energy physics experiment. This is a very low energy. Here we see on the left the positron part, where you see the yellow parts. In the middle, bottom middle of the picture, we see the magnet, where deep there we mix the antiprotons and the positrons, and the antiprotons from CERN come from the right. So I said then everything needs to be very cold, so we will be able to produce and capture the antimatter atoms. And we need to go from the scale of mega electron volt, kilo electron volts, to the scale of less than 1 Kelvin. So we developed over these years of the collaboration endeavor various techniques of cooling the species from brute force, passing the antiproton through degraders, then using the radiation, the synchrotron radiation, and coming into equilibrium with the cryogenic walls as the method to go into the interesting region. And then we do evaporative cooling, and everything needs to be done with very gentle manipulations when we mix the species together. So the first technique that we developed was based on autoresonance excitation. This technique was helped by theoretical endeavor from the Hebrew University group of Lazar and Ido. Over the recent years, we have gone into slow merge, which is slow, as you see in this figure, slowly changing the potential scheme. So eventually, as you see in the D section of the figure here, the antiprotons can be mixed with the positrons without getting further energy. And remember, every milli-electron volt here counts dearly for ability to trap the atoms. Indeed, when we first came out with this Nature paper at 2010, announcing that we succeeded in trapping antihydrogen, the whole season that preceded this paper, we managed to capture 38 atoms, 38 antimatter atoms, and on this small quantity, we based a very severe statistical cuts and demonstration that we did indeed capture the antihydrogen. Since then, we have developed methods that further cooled and increased by a large amount the number of antimatter atoms that are being trapped. What is even more important, well, not more important, but also very important for our ability to come out with physical results, is to add the ability to introduce lasers and microwave into the trapping region and interact with the trapped antimatter atoms in order to see whether we shine them with radiation which is resonant with their transition or off-resonant, and try to make the precise measurements that will be relevant for our quest. So for example, this is how it looks now with the latest addition to the arsenal of measurement tools that we have, putting ultraviolet laser into the vacuum, into the trap, and probe the 1s to 2p transition in the antimatter atom. So the first technique that we managed to apply in order to measure the transitions in antimatter atoms in antihydrogen was of microwave causing transitions between trappable levels and untrappable levels. And I show you spectra, but this is not like obtaining spectra in a spectrometer for light. Here we need to scan the excitation radiation frequency, and for every frequency that we use, see if we're able to take atoms from a trapped state to an untrappable state and get annihilation. So our signal to noise is excellent because we measure just antimatter annihilation. And we are able to come out with such a spectrum here. What we measure here, the separation between these two peaks, is the equivalent of the famous 21 centimeter transition in hydrogen. The small separation between these two green levels that you see in the picture. And this was not the result of 2012. This came 3 years ago with much higher accuracy. The holy grail of accuracy for this topic is measuring the narrow 1s to 2s transition. And here you see what we achieved. And this is the quite impressive accuracy of being able to reconstruct the whole spectrum and determine the frequency to a precision of 5 kilohertz over a transition frequency of 2.5 10 to the 15 hertz, meaning an accuracy of a precision of 2 10 to the minus 12. And all this measurement with this fantastic accuracy so far found no difference between the measured result and the known result from the hydrogen atom. By the way, this is one of the best known transition energy in physics. So here we strive into even increasing our precision and then putting CPT to more and more precise validation tests. The new kid in town in terms of measurements is the 1s to 2p transition. Here you see the whole picture, the whole spectra with the splitting, and we measured, I'll show you in a minute, the transitions here. But what is even more important is that measuring the 1s and applying the 1s to 2p transition and getting a result opens the floor for cooling the antihydrogen atoms for even lower temperatures and being able to capture more of them and make more precise measurement. So this is from this last year, from February of 2020. This is, you see the different transitions of the 1s to 2p. This is with pulsed laser, unlike the 1s to 2s, which was done with CW 2-photon transition. This is pulsed laser with 1 photon, so the precision, the accuracy is less. But as I said, it opens the way for laser cooling in the coming years. The next big endeavor for Alpha will be gravitation measurements, whether anti-apple falls to Earth the same way as an apple falls. And for this, we built a completely new trap, a vertical trap, in which we will be able to measure how antimatter atoms fall. And this is not a drawing, it is a reality being happening now in CERN. You see it as in the process of construction, and we hope to get to first physical results in the summer of this year. So to summarize, since we first trapped the antihydrogen atoms in about 10 years ago, the work of Alpha succeeded in yielding the first measurements of resonant transition in anti-atoms. Actually, the only measurements by any group in the world for this. And we've done it in 3 modes with microwave, probing the hyperfine structure of the ground state, 2012, and then improvement in 2017. With 2-photon CW laser, 243 nanometer, the 1s to 2s transition in 2016, 2017, improvement. And the last measurement, 1s to 2p, this last 3 years. And so far, no difference from the data on normal hydrogen atoms, which I must say, this was expected. The future plans for the next 3 years is further increase the accuracy for all measurement modes, go into laser cooling, and therefore being able to make more precise measurements with many more antimatter atoms, and the first measurement of its kind, gravity measurements, initially at the level of determining whether anti-atoms fall up or down, and then we aim to a precision of 1%. Thank you.
Thank you, Eli. I'm sorry again for not having time for questions, because we're already late. So we just we can move to our next speaker, which is Chilik Frank, who has just returned from postdoc at the Lawrence Livermore National Laboratory. He will tell us about the band method to calculate the non-LTE plasmas. So Chilik, can you share screen? Okay, go ahead.
Okay, I'll share my screen now in just a second. Okay. Okay, everyone can see my screen?
Yeah.
Okay, so I'll start. So yeah, as Ido,
But enlarge, please. So okay, put it in full screen.
it is in full. So you don't see it in full screen?
No. Presentation. Okay. Yes, you can enlarge it.
Just a second. Now can you see the full screen?
Yeah, good.
Okay,
Good.
Great. So first, thank you everyone for listening and thank you for inviting me to talk here. So as Ido presented me, I just returned recently from a postdoc at the Lawrence Livermore National Lab, just a couple months ago, and starting a new venture now. But this work was done at Livermore, so I'll present it, as in my Livermore hat. Okay, so when we speak about multi-physics simulations, what you see now on your screen is a hydrodynamic simulation of a NIF hohlraum. I'll give just really a few words about that. I assume many people in the crowd are familiar with this, but for those who are less familiar with that, the idea is to create indirect drive implosion of a capsule. The capsule, if you can see my cursor, is right here in the center. It's a plastic capsule, and basically you shine the laser. It's a two megajoule laser, which goes into this gold cone. The laser is basically transferred into X-rays, and the X-rays shine on the capsule, creating the ablation process. And this is the laser pulse shape, and so on and so forth. In order to create such a simulation, basically you have to know plasma conditions at each and every point in time and space of this process. And so as you can see, it's a pretty complicated type of simulation. And basically each such simulation can take up to about a month in real time. In computational time, it's way more than that. It's been done on thousands of computational nodes. And each such cell has basically two main components. One is the hydrodynamic simulation, and the other one is the atomic physics simulation. And estimation goes that the atomic physics part takes anything between 60 to 90% of the computational time. So it's a very pressing subject in a sense, and the non-local thermal equilibrium part of this takes the largest chunk of the entire thing. So that's just kind of to give the motivation why doing non-LTE simulations and trying to improve the way that we do them is a very important subject, especially if you want to solve problems like this that are, again, are compiled of many different physical packages, and you want to do it in a timely manner. Okay, so again, more of a general background. How do we make such a calculation? So we said there is a hydrodynamic model and there's the atomic physics model, but how does the loop work? So basically you have the hydrodynamic model, and the hydrodynamic model gives you the temperature. At this point, I'll say the electron temperature and the density at each point in your sample, in your simulation, whatever that is. It could be, any forum, it could be something, a different type of experiment, doesn't really matter for the sake of this discussion. And this, in an LTE case, the LTE atomic model, it calculates the atomic levels and the opacity and emissivity. And what it gives you basically is the opacity, emissivity, and of course the equation of state for this material at these conditions. And then it goes back into a radiation transfer model, which in its turn gives you the energy flux, the radiation energy flux that goes from one place to another, and that goes back to the hydrodynamic model and basically transfer energy from one place to the other. So the important part here is basically that you do get the energy transfer from one place to the other, but the radiation flux itself does not interfere or does not affect the atomic levels because it's at LTE, it's at local thermal equilibrium. When you're at non-LTE, this picture changes quite dramatically. You have the temperature, so the atomic model will give the hydrodynamic model would give the atomic model the temperature, the density, but also the radiative flux that goes from one place to the other. The atomic model needs all those conditions in order to get an accurate result for the opacity and emissivity to go into the radiation transfer model. Now, theoretically, what we would like to do is basically to take this radiation flux and kind of plug it back into the non-LTE atomic model in order to kind of converge this, because the atomic model is, or the atomic population, the level population of the different atomic levels is infected by the radiation flux. However, from a computational standpoint, this is not possible. And as I told you, even without doing that, such calculation can take up to a month, and I'll talk about a few more problems with this in a second. So basically, our problem is in two folds. First of all, when we try to do this, and we try to do this in line in order to get the radiation flux correctly, and again, the radiation flux can be totally non-thermal. We don't know, we have no previous knowledge about how this radiation profile looks like. And again, can be very different from one case to the other. Then we need to kind of make a lot of compromises in the way that we do the non-LTE atomic model, which in a sense gives us a much oversimplified model that gives us not such great results. So the radiative properties themselves are evaluated exactly for the specific the specific plasma conditions, and it's at this point it's mostly done in line. So, but the price that we pay for this, if you want to say quote unquote, is that we have to take a very oversimplified model in order to do this in a reasonably timely manner. So the problem with that again is, okay, even if we do this, are those results even reliable? What we would have liked to do is to kind of put this into a table, because if you look at the LTE cycle, once you know that the atomic model only depends on the temperature and density, what you can do and what you mostly do is you basically create a table for a big set of temperatures and densities that are relevant for your experiment, for your conditions. And then while you do the hydrodynamic model, you just do a table lookup, which is very fast and easy. We would have loved to do the same thing for the non-LTE atomic model, but that, of course, again, is not really possible, because if you just look at the radiation field usually in a hydrodynamic model, let's say in a simulation like I just showed before, is characterized by about 200 parameters, so 200 radiation groups. So that will, of course, give us an almost infinite number of table points if we want to actually tabulate the entire thing. So the idea here, and kind of the mission I set up to try to solve here is, okay, so how do we take the 202 dimensions and reduce it into something which is manageable? So again, just as a quick word of, what's, LTE versus non-LTE. So LTE, as I said, local thermal equilibrium, means basically that I can assume that the plasma has at least at a local, but in a macroscopic sense, it has can be assigned with a temperature. In a non-local thermal equilibrium, versus a non-local thermal. In LTE, the plasma has a single temperature, or either it's because the temperature of the density and the radiation is the same, or the plasma is so dense that its collision is dominated, therefore it's at LTE. And the thing is, even more so, like in the case of the hohlraum, we would like to use the LTE models when the plasma is indeed in LTE conditions. And a lot of the, let's say, the hohlraum material is actually at LTE conditions. So we would like to use those when it is reasonable to do that. And even though again, theoretically, the non-LTE models should converge into the LTE result at LTE conditions, since they make different assumptions and different simplifications to begin with, of course, we would like not to use them when we don't have to do this. So again, just to summarize kind of the differences in what we're looking for. So in LTE, we definitely can assume that the plasma is at steady state. Okay, but in a non-LTE in general, plasma might be or might not be at steady state, even though for the sake of what I'll go and show you in the following slides, we do make that assumption, and it's usually good for the cases that we're interested in, but in general, one should remember that does not have to be true. In LTE, electrons, ions, and radiation, if it is at all important, are all thermal. In non-LTE, in the most general case, again, none of these have to be thermal. Each have an independent energy distribution, which might be thermal and might be not. Again, for the sake of what I'll go and show you later, we do assume that the electrons are thermal, but again, but their temperature does not have to in any way match the radiation field profile. Again, in LTE, not only that it's thermal, we can assume that all the three species can kind of have the same temperature, or at least in the case of dense plasma, the radiation temperature doesn't really matter much. And again, in the non-LTE, specific species can have a thermal distribution or not. Again, and the good thing about it in LTE is that you can use the Saar-Boltzmann distribution to solve the radiation population. On the other hand, it's very highly correlated plasma, so making those calculations is quite difficult. And there's a very large number of states that you need to take into account in order to actually get the population distribution right. In non-LTE, the kind of bad part, the bad news is that you need to calculate all the transition rates, all the atomic transition rates. And the number of states, that's a very big debate until today. How many do you really need in order to get this correct? The reason that we would like to use LTE models when they are applicable is that you do need a very large and sophisticated model for that. And in that case, you can calculate the atomic potential even for the calculated plasma conditions. While in non-LTE, even best codes have to pre-calculate the atomic data, the atomic potential, and the energy levels, and they don't do that, and they don't do this per plasma conditions. So there were a lot of attempts how to tabulate non-LTE plasmas, or non-LTE, not tabulate non-LTE plasma, tabulate radiative properties of non-LTE conditioned plasmas. The first and the simplest attempt, which is for some applications, it's actually not very bad, is just to use LTE-like tables and just neglect the radiation. So you solve a non-LTE model with assuming the radiation plays no role, and the only thing is that it's not in equilibrium, so you don't have any temperature. You can do, there's a whole other section where you do add radiation parameters, but only for a very limited number of strong lines. In this case, what you're assuming is that the radiation doesn't carry much energy from one place to the other, but it does affect the population distribution, which is not the case in things that we are interested. Again, this is the case of the hohlraum, where a lot of radiation is actually carried by the radiation, and therefore you cannot decouple that. There is a whole different effort which is called the linear response term, which is kind of making an approximation of the radiation field effect, and which I won't get into here. And then what you all can also do is, but the problem, and the main problem with this approach, or any approach that does it, or I skipped the one approach, which is representing the entire radiation by a single effective temperature parameter, which is basically just summarizing the entire energy and taking the fourth root and getting a temperature and basically neglecting the distribution of the energy, of the radiation energy. And the problem with those approaches, both two last approaches, is that you need to know something about your radiation field in the case that you're working with, let's say the hohlraum, in order to make this approximation in any way accurate or close to accuracy. So how much time I have?
2 minutes. So
2 minutes. Okay, so I'll make it in 2 minutes. So the idea here is actually very, very simple. Now I get to the solution. The Benz radiation method just assumes one thing. It just makes very simple assumptions. We assume that the response of the material to the radiation field only depends on the bands or the shells that are active in those conditions. So what we do is we use averaged fields just in those bands. So let's say you have a carbon plasma, so it's only the K shell and the L shell that can even be considered as responsible for that. And the algorithm is very simple. You make the calculation with no radiation field. You see what shells are active, and this is, of course, does not make no assumptions about what the radiation field is going to be. And then you just can tabulate what would happen with different radiation fields, again, constant in those regimes. And I'll just show one example. Let's say we take a copper plasma at the temperature of 1 kilovolt and given electron density, we calculate it with no radiation field. We get a ionization distribution of some sort, and we calculate the opacity, emissivity, the radiative properties of this plasma. We get two bands. In this case, the L shell, again, the L shell and the K shell for copper, which are kind of generally presented here. And then we say, okay, what would happen with a more general radiation field? And in this case, I took something which is kind of representative of again, a hohlraum-like radiation field, which is something which is kind of a thermal radiation with some kind of a more hard X-ray component to it, which is what we find a lot of the times in hohlraum calculations. And what you can see on the left-hand side is the radiation field in three different ways. One is the blue curve is the actual radiation field that was kind of assumed here. Again, it's invented, but just to make the point. The green line is what would happen if I just take the same thing and assume an effective temperature. And the red line is what I put in for the bands method. So these are the two bands that I got from no radiation case. And then I just take a flat top radiation at both ends. And this is this plasma source function. So it's opacity over emissivity over opacity. It's just to show both on the same plot, but it's the same for if I showed opacity and emissivity separately. And you can see, of course, if you make the calculation with no radiation field, you get very far from the actual result. The effective temperature does get you closer, but still, there are quite a few orders of magnitude here. And then if you took the band method versus the full actual detailed calculation, which is what would have happened in line, you actually get a pretty good approximation for the source function.
Okay.
And so I'll skip all the other examples, but the basic idea is that it gives you a way to make a tabulation really, really quick and simple. And hopefully you will get into the actual codes pretty soon. And with that, I'll finish.
Okay, thank you very much, Heli, for a very interesting talk. And we just move forward to our next speaker, which is Omri Chano. Can you share screen, please? From a Technion, will tell us about 2D peak simulation on the narrow channel hole thruster plume. Omri, the stage is yours.
Thank you. Can you hear me?
Yes.
Okay, so today I'll talk about a 2D particle and cell simulation of the narrow channel hole thruster. So first of all, I want to talk about the need for low power electric propulsion, or EP in short, which is a kind of rocket propulsion, usually involved with creation of plasma and accelerating it with electric and magnetic fields. So today, nanosatellites are becoming more popular for space mission because they're very cheap to launch. They require a propulsion system in order to perform a variety of space missions, such as communication, Earth observation, etc. Ideally, we would like to use the efficient EP devices for propulsion. However, the power supplies in nanosatellites is limited to below 30 watts. So there are only limited plasma propulsion solutions available for these power levels. Ideally, we would like to use devices, popular EP configurations such as hole thruster, which are very mature and have a long heritage of use in space. But however, the performance drops dramatically for hole thruster with power below 100 watts, and there are no reported operation below 30 watts. So the Aerospace Plasma Laboratory at the Technion develops a new concept called the narrow channel hole thrusters, or NCHT in short. Here we have a photograph of the NCHT in operation. We can see here the blue plume of the xenon plasma. These are some typical performance figures for the NCHT for several scenarios. Here we have the mass flow rate of the xenon in milligram per second, the discharge voltage and the discharge current, and typical thrust of around 1 millinewton, and typical power consumption of about 20 watts. So let's talk a little more about how the NCHT works. Here we have a schematic cross-section of the NCHT. It has a cylindrical symmetry, and this is the cross-section. This is the axial direction. This is the radial. This is the channel where the plasma is created. So this is the interesting part. We have neutral gas coming from the anode this way. The anode is held at high potential. And we have electrons emitted from an external cathode placed outside the channel. The cathode is held at a low potential. So we have an axial electric field together with a radial external magnetic field generated by electromagnets. We have the electrons drifting in an E cross B drift in the azimuthal direction. That lowers the axial conductivity of the discharge and therefore helps to create increased ionization. And the ions created in the channel are accelerated outwards to create thrust. That's how we get the thrust. So this description is common for many hole thruster, but the NCHT has some unique features that allows it to operate in low power levels. All of these features aims to increase the ionization efficiency using a small channel volume. Basically, we want a current density of about 1,000 amps per square meter, which is similar to conventional hole thruster. The diameter of the NCHT is 30 millimeters, so it's very small. The annular channel walls are made of metal, held at cathode potential. We have a decreasing cross-section of the annular channel towards the exit. And we have a very small dimensions. The length of the channel is only 2 millimeters from the anode to the exit plane, and the width of the channel is only 1 millimeter at the exit plane. And we're also using a very low voltage, usually below 100 volts, to maintain low power consumption. So recent probe measurements show that the NCHT discharge develops significantly outside the channel, which is fairly uncommon for the hole thruster. Previous hole thruster simulation in our lab using the ZUPIC APL particle and cell code didn't consider the plume region. So an important question for our research is, how does the discharge parameter are distributed inside the NCHT channel when the plume is imported and we take it into consideration? So that's why we constructed a numerical model for the NCHT that includes the plume region. We're using a particle and cell 2D simulation in the radial axial coordinates. We're using a 2D simulation because the computational cost of peak simulation is very high and it's only feasible in 2D with our current computational resources. So what's happening here that we're solving the electrostatic problem, meaning that we assume constant magnetic fields. And then instead of solving the Maxwell equation, we just solve the Poisson equation. So we have a boundary condition for the potential here. At the anode, the potential is the discharge voltage. At the metal walls, the potential is the cathode potential, which is phi equals 0. at the right boundary, we have the cathode potential phi equals 0 and the electrons emitted from here to model the cathode operation. On the radial direction, we have boundary conditions of far field, meaning there is no change in this direction. And we're also modeling the electric alumina layer outside the thruster, preventing the electrons from going straight to the metal walls and actually force them to go inside the channel. So this is the model. The electrons, ions, and neutrals are modeled as kinetic particles and not as a fluid. We're using the Monte Carlo collision model, or MCC in short, to model important collision processes such as ionization, excitation, etc. And we're also modeling wall interaction. As a first step, the cathode is modeled as a constant current. Obviously, in reality, there is a coupling between the cathode and discharge, but as a first step, that's a fine, crude model. These are some of the parameters that we're using for the simulation. We're using xenon gas. These are the dimension of the domain. This is the electron injected electron temperature in EV, the time step, the number of cells in each axial and radial direction, and this is the duration of 10 microseconds for the simulation to reach a steady state, and the discharge voltage that we're using. So first of all, we wanted to compare the global parameters we got from the simulation to the one we see in experiments. So roughly for the same scenario, we see that the current, discharge current, which is basically the electron current going to the anode, is the one we see in the simulation is about half of the one we see in experiments, and consequently the power as well. So we need to understand why. So we dig in a little deeper and compare not only the global parameters, but 2D spatial parameters of the plasma, specifically the plasma potential that in experiments we measured using an emissive probe, and the ion current density that in experiment we measure using a planar Langmuir probe biased to -60 volts. So we want to compare the two, the experimental results and the simulation. So here for the plasma potential, we have the simulation results in red and the experimental results in the plume in blue. The exit plane is marked with a black dashed line. So we can see that the main acceleration region in the simulation is obtained in a thin layer outside the channel, which is surprising. And also for the ion current density, we see that both in the simulation and experiment, actually the maximum of the ion current density is outside the channel, which is also surprising and not common for a Hall thruster. Usually it's inside the channel. Here we can see the ion current density from the simulation in 2 dimensions, and also the ion streamlines in the white lines. And we can see here as well that the maximum ion current density is obtained outside the channel. And you can also see that there is some ion backflow to the electric wall, which is a loss mechanism that we need to consider. Here we also have the ion number density in log scale in 2 dimensions from the simulation. We can see a significant ionization occurs inside the channel, but there's also a second ionization region that develops after the acceleration region outside in the plume. So to summarize, the NCHD discharge was analyzed using a 2D particle and cell simulation that includes the near field plume. Some important insights from the simulation are that similarly to experiment, we observed that the NCHD discharge is pushed out. We see that the acceleration region is a narrow region immediately outside the channel, and the significant ionization is obtained inside the NCHD channel, which is important for the thruster operation. There is further study that is required to determine the parameter influencing the anode current and why we see a lower value in the simulations. We need to learn how the numerical parameters, in particular the parameter that we're using for our anomalous transport model, is influencing that current, and also how we model the cathode. we also consider extending the domain in our simulation because we see a more gradual change in the experiment, suggesting perhaps a larger domain is needed to simulate the plume of the thruster.
Thank you. Thank you, Omri. So again, we don't have time for questions, but please feel free to contact the speakers and you can ask questions, continue discussion elsewhere. So now we are fast moving to our next speaker, which is Meital Simantoff from the Technion. And please, Meital, so go ahead.
You?
Yes.
Yeah. Just a second. Okay, thanks. You see the screen?
Good.
Okay, so the title of the presentation is a generation of periodic bunches produced by a squeezed electron beam in a resonant cavity. This work was done with collaboration with Dr. Johann Leopold, Dr. Yorav Bloch, and Professor Yaakov Krasik. And in this slide, I want to give a short introduction. What is a squeezed electron beam? So to understand it, we need to first define the limiting current that's supporting a steady state flow of a magnetized relativistic electron beam in a cylindrical diode. The limiting current is defined by the energy of the electron, the radius of the electron beam, and the radius of the anode. For smaller anode radius, we get a higher amplitude for the limiting current. This is the formula for it. Now let's look on the case when we have an tube, which is a combination of two different radii, R1 and R2, when R2 is the largest one, and a beam is emitted in the narrower tube with radius RB and injected into the wider tube with radius R2. If the injected current exceeds the limiting current of the wider tube, then we get a formation of a virtual cathode in the radial transition of the anode. And from this location, part of the electron reflects into the narrower tube and form a virtual cathode near the emitter, which screens the electric field on the surface of the emitter and causes to reduction in the emitted current. And from the location of the first virtual cathode, the other electrons continue the forward motion through the downstream end flange of the system with amplitude current that's equal to the limiting current of the wider tube. Now, if we increase the injected current to be higher than the sum of the two limiting current of the tube divided by 2, then in this case, electrons that moves between the radial transition of the anode and the emitter slow down due to repulsive force between the electrons, and we get a space-short cloud with a high density of electrons and with low kinetic energy. And this is called squeeze state. Now, our motivation in this research is to find a way to force the electron that moves between the emitter and the radial transition of the anode to oscillate rather than relax to a squeeze state in order to obtain a high-frequency modulated electron beam, which can be used for generation of high-power microwave. Okay, this is the setup that we suggest. Distance between the, we have the coaxial anode cathode system. Distance between the radial transition of the anode and the emitter is 20 millimeters. We connect a reflector. A reflector was connected to the cathode using a central rod, and therefore the potential of the cathode and the reflector is the same. Behind the reflector, a collector was attached to the downstream end flange of the system, and the distance of it from the radial transition of the anode is defined by DC, the length of the cavity. We apply the negative high voltage pulse of the cathode with amplitude of 150 kilovolts, and in the system, we have also an axially uniform magnetic field with amplitude of 1 Tesla. Now, let's look on the first case. We don't have a collector in the system. We calculate the emitted current, the total current, which is the current that's collected on the upstream flange of the system, and the collected current on the downstream end flange of the system. This is just I want to emphasize that it is a result of simulations, okay? In this case, electrons emit from the emitter and inject into the wider tube, generate a virtual cathode in the radial transition of the anode. And from this location, part of the electrons reflect into the into the to the narrower tube, reach the emitter, screens the electric field, and causes to reduction in the emitted current. And you see that we see this moment here in the signal of the collected of the emitted current. Other electrons continue their motion flow through the reflector, and in front of the reflector we get a space charge that accumulates there. And from this location, if the absolute potential of this position when we have a space charge is higher than the potential of the reflector, then part of the electrons can penetrate the reflector and accelerate through the downstream end flange of the system. And then we get the signal of this of the collected current. At the end, we get a squeeze state between the reflector and the emitter. Now, the second case, when we have a collector in the system, the behavior of the collected current is up to 60 nanoseconds is the same as in the first case. But after that, we get modulations in the collected current with high frequency and with high amplitude. The source of those modulations is, as you can see here in the figures of the phase space, is of the squeeze state. The squeeze state between the reflector and the emitter acts as a current source, and we get a release of electron bunch from the reflector that reach the collector. To understand the reason for those modulations, we studied the system also for different value of the cavity length. Okay, cavity length is the length of the wider tube, and those are the value. We simulate the system in the absence of the electron beam, and we checked what is the eigenfrequency of the cavity, and those are the values that you see here in the table. And then we repeat some simulations in the presence of the electron beam, and we checked what is the frequency of modulations that we get in the collected current. Up to the time run simulation, no modulations appear in the collected current for DC equal to 11 centimeter. And then we conclude that the current modulations develop when certain relations between the electron transit time and the cavity eigenfrequency are satisfied, because we get we get values that are very close, okay, in the absence and in the presence of the electron beam. Okay, based on simulation result, we design our experimental setup. The electron beam is emitted from the explosive emission plasma that form at the surface of a carbon fiber-based cathode, which is here. Distance of the emitter from the radial transition of the anode was 22 millimeter. Reflector was connected to the cathode using the central rod. The reflector has finite transparency. To measure the collected current, we have a Faraday, cap, and we also measure the total current using a Rogowski coil that was placed at the output of the generator. And all the system was assembled in a solenoid that produced an axial and uniform magnetic field of 1 Tesla. Those are the experimental results for a specific gap between the anode and the reflector, and specific gap from the gap between reflector and Faraday cap, and cavity length of 16 centimeters. You see that in the signal of the collected current, we get we receive modulations. Those modulations suggesting the existence of the electron bunch. Each bunch has a duration time of 2.5 nanosecond. FFT of this signal gave us dominant frequency of 204 megahertz. We repeated on the experiment also for difference gap between the anode and the reflector and Faraday cap, and different lengths for the cavity. And all the time we get the same dominant frequency for the modulations in the collected current, which is 200 megahertz. Okay, so now let's compare between a simulation and an experiment. In both of them, we get modulations in the collected current, which means that we have electron bunches in the system, but the amplitude of the modulations and the frequency were not the same. In simulation, we get higher frequency of 1.13 gigahertz, while in experiment, we get 200 megahertz. So we start to think why we have a discrepancy between the two, and we thought that maybe we didn't model the all experimental condition that we had in our experimental setup. So we repeated on the simulation, and we add in part of those experimental condition. First, what we had is the large cavity that connect between the generator and the system. It's a cavity it's in the upstream side of the system. And we also add a finite transparency for the reflector, and we change the magnetic field profile to be as the major magnetic field along the z-axis in the experiment. Okay, result of these simulations is here. You can see here the signal of the collected current. We get a modulation, but with smaller amplitude, and the spectrum of this signal gave us a dominant frequency of 1.9 gigahertz, and also two low component frequency. Those components are very close in their values to the eigenfrequency of the upstream cavity of the large experimental chamber, this chamber. So adding those conditions decrease the discrepancy between simulation and experiment. Okay, summary. So the experiment has been successful in producing a periodic terrain with amplitude of 40 amperes. Each bunch was 2.5 nanosecond, and frequency of the modulation was 200 megahertz. In the simulation, we get also modulation, but with higher frequency of 1.13 gigahertz. Experiment result did not show sensitive to change in geometrical parameter of the system, while in simulation, we saw that the frequency of modulation changed when we changed the length of the cavity. And by adding, changing a little bit the simulation by adding part of the experimental condition that we have in our experimental setup, we decrease the discrepancy between the two, but still we left with some difference. And this can be because the experimental emitter is significantly different from that simulated, because it's produced radially expanding plasma, from which electrons are emitted in both axial and radial direction. And also, simulation do not reproduce parasitic emission of electron from the reflector and its ring type holder, and as well as ion flow from the plasma that form at the surface of the anode downstream flange. Thank you.
Thank you, Mital. So again, we don't have time for questions. We can contact her separately. So we just continue to after Mital, our first Tal. So will be another Tal after that. So let me introduce Tal Keller from the Whiteman Institute. So Tal, please go ahead, can share screen, go on. Good.
Okay. See my screen? Okay. So hi, very happy to be here as usual in this in the Israeli Plasma Conference. I will speak about experimental work, magnetic field measurements, and current distribution measurements of at close to stagnation and imploding Z-pinch, gas puff Z-pinch. Okay, so this work is done with our collaborators in the US, but I will what I'll present now is only the experimental work done here. So these are the parameters, this is the machine, but the main thing I want to say about with this slide is that t equals 0 is the time of stagnation, which is characterized by X-ray yield and current turnover, which is we call it a notch. It's like a dip in the current profile. All the rest I'll skip because this is a short talk. Okay, so why do we want to measure the magnetic field? We have a lot of motivations, but the main ones are because it is the main driving force of the implosion, obviously, the J cross B force. It will be very significant in determination of the energy available for compression, which is, of course, it holds a very large portion of the energy, and determination of the ohmic heating by determining the current flowing in the plasma column. So there are a lot of other motivations like instabilities, knowledge about instabilities and all kinds of stuff, but these are the main ones for now. This is our setup, the cathode, the anode, and actually this is what we, this is the two-dimensional projection of the plasma cylinder. And there's also somewhere in the middle, anywhere we want, we choose a Z position, and we also extract the spectra of the plasma. So we combine these two measurements, and the main thing I'll show you today is the measurements in the Z positions, which are now circled in red, 9 to 15, which were not measured until now, and always gave us some doubt about our conclusions. And now, since we measured them, we have very little doubt about our conclusions, which I'll talk about. So these are the previous results achieved by Guy Rosenzweig, a former student in our lab. And well, the astonishing thing was that most of the current flows outside of the imploding plasma column, even at times close to stagnation, even at -2 nanoseconds, as you can see, -3. So the current itself does not implode with the main plasma. This was a surprise, but still we had doubts. Why did we have doubts? Because as you can see, no measurements were made in small radii anywhere, because it was impossible experimentally with the old system. And another place, another volume of the anode-cathode gap which was neglected, which was not seen, is the anode recessed volume, which is marked here in red question marks. So we had a good knowledge about the magnetic field and current distribution in these 9 millimeters of the gap, but none in these 6 millimeters of inside the anode. And also, we didn't have any measurements close to the axis anywhere in the gap. So by making our light collecting system much more efficient and buying some new spectrometers, we managed to to get our measurements in very, very short exposure times, less than half of what we used to expose. This revealed a structure in the ion, in the imploding ions. They don't just they do not spread continuously over all radii, but they live in certain radii positions, and this enabled us to get much more accurate measurements, because it enabled us to get conclusion without doing inverse Abel transformations, which enter some uncertainties and made our conclusions less strong. So we got these measuring points, a lot of measuring points in each shot, which helped in our conclusions. So this is how we did it. We opened a window like that in the anode. This enabled us to perform the same measurements we did in the main gap, also on the recessed gap. And well, first we saw that, as expected, the implosion happens in this volume a little bit before it happens in the main gap, but this was expected because we see this phenomena of zippering also in the main gap. But the main thing is, as I said, we got a lot of measuring points. And as you can see here, this is a spectrum, and we see the rings here. Here marked with red dots in different radii. And these enable us to get many measurement points and relatively accurate measurement points. And we saw that indeed, as we thought but had no proof, throughout the entire implosion, no current runs through the main plasma column. Not in the main gap, not near the axis, not in the recessed area or volume, and also in later times. Okay, so as you can see, this shot here gave us 1, 2, 3, 4, 5, 6 separate measurement points of the magnetic field and the current, of course. And as you can see here, this is the stagnated plasma, as you can see it also in the imaging, the filtered imaging. And this is the current, and we're talking about stagnation itself, -2 nanoseconds before stagnation. And still, most of the current, almost 80% of it, lies outside of the main plasma column, and less than 10% is actually flowing the stagnated plasma. Now we can be sure. I'm finishing. Okay, we always had the feeling, and our measurements, because of our measurements, we always had the feeling that this is the situation, but now we can say definitely that no current or very, very little current flows in the stagnated plasma. And this has a lot of implications which are far out of the scope of the time scope of this talk. So I hope you'll hear about them soon. And thank you. This is it.
Okay. Thank you, Tal. Very interesting talk.
Thanks.
Okay. So let's move to our final speaker. So it's the second Tal. Hi, Tal. Who is my student, actually, working with also with Ilan Be'eri from Rafael. And okay, Tal, so please start. Okay, you start from the end, I see. Good.
Does it work? Tal Keller, please stop sharing your screen. 1 second. Yeah.
Wait, Tal Keller, can you please stop sharing? Okay, so let's see if I can override that. Okay, good. Okay. That's good. Let's enlarge it. Okay, so you have 10 minutes, so it's almost about time. I will leave time at the end of the session, so we don't have official time, but if people want to stay and talk and chat, so it's good. So I will keep the session open until for people to stay and talk if you wanted. So okay, so now Tal, please get started.
Okay, so hi, I'm Tal. I'll be presenting work I've done with my collaborators, Ilan and Ido. Ido being the chair of the session and my PhD advisor. The work is titled The Rate Equations Model of Multiple Magnetic Mirror Systems. So our ultimate goal is to create a fusion power reactor. This requires to contain hot plasma for long enough. The way to go about this is use magnetic trapping. Toroidal systems such as tokamaks are the popular variant, but they are quite complex. Linear systems, which are magnetic mirrors, are simpler, but they have a major flaw: axial loss of the plasma through their loss cones. Our goal is to reduce the outgoing flux from the magnetic mirror. Many methods were proposed over the years. One is using multi-mirror plugs. So if you look in the schematic, we have on the left the main cell, which is the magnetic mirror, where in the would-be reactor, we would have our fusion plasma. Particles, ions, would escape through the loss cone, and we want to stop them. So in the multi-mirror approach, we chain together additional magnetic mirrors to form the multi-mirror section. And the way it works is that as ions escape the main cell, they have multiple opportunities to get scattered and get trapped in one of these cells. So in the limit of many cells, the dynamics approach one-dimensional diffusion. And as you add more and more cells, you inhibit the outflow. The optimal performance of the system is when the scattering mean-free path of the ions is on the order of the cell length. The way to intuitively understand this is looking at the limits. If the mean-free path was very, very large, then the particles escaping the main cell would never get an opportunity to get scattered and would just escape. In the other limit, if the mean-free path was very small, then the particle would get scattered many times, and the assumptions of the magnetic mirror trapping particles in the radial axis would not apply. The mean-free path of the ions depends as the temperature squared over the density. In previous literature, it was mostly assumed that the plasma was isothermal. However, we can also consider an analogy where a fluid that flows through a tube pressurized at one end. As it flows and expands, it can cool down. This might also happen in a plasma, which is not unlikely because in the main cell, we inject hot particles, and in the end of the multimirror section, we have cold plasma. So a temperature gradient is possible, and several experimental works shown things of this sort. This cooling effect is treated in our model for the first time. We predict that toward the end of the multimirror section, as the plasma flows toward it, in the isothermal scenario, as we can see in the equation, if the temperature is constant and the density goes down towards the end of the multimirror section, the mean-free path increases, we have less collisions, and we get worse confinement. On the other hand, in the cooling scenario, the temperature also goes down, and overall the mean-free path decreases, so we get more collisions and better confinement. So now let's talk about our rate equations model. Our model is quite simplified. It only deals with the axial dynamics. We divide in each one of the cells of the multimirror section, we divide the phase space into three: the particles that are captured or trapped, and the particles that are in the loss cone. We have two kinds, those that go to the right and to the left. So in total, in a given cell, we have the density of the captured particles and the density of the particles that go to the right or to the left. Our rate equations discuss the relations between them. So within a given cell, Coulomb scattering can transform particles from being trapped to being lost, and vice versa. And the particles that are in the loss cone, they get transmitted from one cell to the other, where the right-going particles only go to the right and the left-going particles only go to the left. This is schematically how our model looks like. Here, I'm also showing how what the actual equations look like for a given cell, but I will not go and discuss each term. But this is how it actually looks like. So for every cell, we have 3 densities, and for a total of n cells, 3 n equations. We search numerically for the steady-state solution where we inject particles, hot particles, from the main cell into the multimirror section, and we want to find a steady state where the total flux in the system is constant and the time derivative of the densities is 0. We can make this solution when we assume different things about the temperature. So the first will begin with the diffusion model, which is the black line. So once again, in the plot, in the y-axis, we have the total density, and on the x-axis, the cell number. The diffusion model would predict in one dimension that the density should decrease linearly. And in our model, when we assume a constant mean-free path in the system, which is not a very realistic assumption, the density does go down linearly. In other assumptions, which are the isothermal assumption in blue, we get a nonlinear solution. And when we make several assumptions on a cooling scenario, we have 3 of them, we also get a nonlinear solution, and they look different. So these are signatures that could be tested experimentally. So this is how the steady-state solution looks like. But what we are really interested in is the steady-state outward flux. This determines the confinement quality. when the flux is lower, we have higher confinement time. But from this plot, it is not trivial to deduce what is the outward flux, because the flux is given by the right-going particles minus the left-going particles, which I'm not showing here. So to conclude, we developed a rate equations model for the multimirror system and solved for the steady state. Compared to the diffusion model, our model predicts that the multimirror system performs worse in the isothermal scenario, which is commonly assumed. We treat the possibility for a cooling plasma as it flows for the first time and predict it performs better than the isothermal plasma, and better it means by up to an order of magnitude. The different scenarios we tried differ in their prediction for the steady state density profiles inside the multimirror section. This can be tested experimentally. For future work, we intend to study the temperature profile in the multimirror system and attempt to use RF fields to improve confinement by attempting to reduce the outward flowing loss cone. Thank you.
Okay, thank you, Tal. So you're actually just in time, so as should be the 3 and 10 minutes. So officially the session is closed, but I will leave it so a few minutes. So if people want to talk about some of the talks and questions, have some discussion. So I'll leave it open until the last member will leave. But officially the session is closed. I want to thank all the speakers. And hopefully next year we have in-person conference. So thank you again. And please, so can you unmute yourself and you can talk and say goodbye and hello. Thank you.
Great to see you. Can I ask the last speaker?
Yes, sure.
You said there is cooling. What is the source of the cooling, and doesn't it counter? Isn't it not that good that you cool? You want to confine particles and also energy.
So a source of cooling could be adiabatic cooling, same way as a fluid in a tube can cool down. Whether it's good or bad, where in our case it's good, because as the temperature goes down, the mean free path for scattering decreases, so we get more scattering, and this improves the confinement overall. We don't care that the temperature itself is low, because in a would-be fusion reactor, the fusion would only happen significantly in the main cell. The outer cells that constitute the multimirror section are only there to reduce the outward flow.
Okay. Thanks.
You get some cooling, but also the density goes down too, right? That'll reduce the collisions. But overall, you still have some net decrease in collisions.
Yes, these are the several cooling scenarios we tried. If we assume the plasma has just if the equation of state of the plasma is just ideal gas, then you need to pick how many dimensions, spatial dimensions, does the plasma exist in, cools down, expands in. So these are the different plots I showed, where we tried 1 dimension to 3 dimensions, where 1 dimension is the most logical one if you assume simple adiabatic cooling. So in that case, in all the cases we tested, the total mean free path goes down, even though as the density goes down, when the density goes down, it pushes the mean free path up, but the temperature going down pushes it down more, and it wins.
Right. Did you try if each of the cells has a potential, so then the plasma will rotate? That'll extend your mean-free paths, among other things.
Can you elaborate?
Well, I'm just thinking that if each of the cells, I mean, you can have a regular mirror, but not have the cells at any potential. And if you put it at a potential, then you'll get an extra confinement in each cell, right? Because you got the centrifugal potential. And you'll also lengthen effectively some orbits. I'm not sure what it'll do, but maybe something to think of. I don't know.
Well, our model was quite simplified, and if you have some good suggestions, I would love us to chat some more together with Ido.
Oh, sure. Okay.
Yeah. Okay.
It might be the same as introducing some decelerating voltage in the other cells, then effectively creating even cooler ion temperature. Is that what you meant?
It's not what I meant, but it would probably be something that would happen. I mean, something along those lines, because you basically have another potential from the centrifugal potential.
Yeah. So there's a lot of ideas how to improve that, because just this, our simple model does not help so much. So we do want to increase the collagenality in the other cells. We should try to find ways to do it to improve the efficiency of that. So this is the beginning of the work.
Right. Good. Cool. Yeah.
Okay.
Thanks for
any other questions on other talks? So please feel free to speak.
Is Meital still there? I only see these squares.
I'm here.
In your talk, you had an axial magnetic field. Axial magnetic field, that's the only magnetic field that you have. And the electric field is either radial or is only radial, right?
Radial and axial, I can say.
Axial, also along the field.
Yeah, two components for it. Yeah.
But the particles do not cross field lines, right? They just move along field line, or they do rotation azimutally, right?
Right. Yeah. It's a confinement. Yeah. The electron beam is magnetized around the lines of the magnetic field.
So how can they move far away radially from the axis, from the cathode? It's only a Larmor radius.
You mean in the back side of the cathode?
Anywhere. I mean, that's they are emitted, then they move through the reflector towards the collector, but they move only axially and radially. They only maybe traverse radial Larmor radius, one Larmor radius. Is it so?
I mean, inside, between the reflector and the emitter, we have the electron beam. But if we have a squeeze state, so it's like a cloud. It expands in the radial direction of the system, because the high density of electron that we have there. It's not an electron. This is what you mean? Yeah.
Yeah, I'm asking how the electrons cross field lines. If I apply a large radial electric field and magnetic field, usually I'll just have a rotation, unless I cross field lines. So I wanted to understand if they really cross field lines radially.
They have, I think they have a component of radial velocity in the system. Because if they have, let's say, a radial component of electric field and an axial component of magnetic field, so you have V theta, okay, E cross B. And if you have V theta cross BZ, so you get a radial component of a force. So there is, let's say, a radial component of a force that...
usually you don't get this, but you see it in the simulations, right?
It came also from the electric field of the electron himself. I mean, if you have a bunch of electrons there, so you have a dominant electric field, and this one is a radial radial force. I mean, that Understand?
Well,
You have a
this is a geometry of a magnetically insulated diode, right?
Yeah.
So the electrons should acquire some Larmor radius, relativistic maybe. If yeah.
Yeah, it's relativistic.
Depends
Yeah,
on the
it's
voltage.
200 kilovolts.
Okay.
I think that the cloud of space charge between the emitter and the reflector, I did also experiment after this experiment that I present, it's expand in the it's expand, okay? We checked it. And
radially.
we saw, yeah, radially. And I also estimate the radial expansion of the cloud of this space charge. So we saw it. And okay, so in the presentation, we also saw that the electrons reach the wall of the anode in the backside of the cathode because of the magnetic field lines. So this is not because of the electron's beam, the electric field of the electron beam. It's because of the lines of the magnetic field that is closed on the wall of the anode in the back.
So the magnetic field lines are not just axial.
In the system, yeah, where I have the cathode, the reflector, and the collector, yeah, it's in axial direction, but you know, the lines are closed outside.
Mm-hmm.
Yeah.
Oh. Okay, thanks.
Okay.
Well, I just have a general comment that it's wonderful to see everyone, at least to see everyone face to face, not face to face, but virtually, including Nat from far away and all of our colleagues that are closer. And just hope that soon we can actually meet face to face and not just virtually.
Great to see you, Ruben.
So no further comments. So I say Happy Hanukkah, all of you.
חנוכה שמח, להתראות לכולם.
Yeah. I'll see you next time.
Hey, Chag Orim Sameach.
Chag Sameach. Thank you. Thank you, Nat.
Bye.
Bye.
Okay.